Hello all, welcome to this next lecture in this course on time series forecasting with applications in R. Just to summarize very quickly as to where we stopped in the last lecture. So, I guess we talked majorly about concepts like stationarity, which are very important in analyzing any time series data. And in today's lecture, we will kind of explore more about stationarity through some examples and then exactly specify as to how one can show that a time series model is indeed stationary or not. And then we will kind of blend in the idea of non-stationary series, because as mentioned in the last lecture also, almost all the practical examples that we see around, they possess some trend or some repetitions or some seasonality in themselves, making the series to be non-stationary. And just to summarize again, the last point that we talked about in the last lecture is that different types of stationarity. So, we pressed upon strong stationarity in the last lecture, and then today we will start with another kind of stationarity which is slightly more important than strong stationarity, which is called as weak stationarity. So, what exactly do you mean by weak stationarity? So, you have other alternative terms for weak stationarity also, which are called as covariant stationarity or stationarity in a wide sense. Alright. So, either weak stationary process or covariant stationary process, or in general one can say that time series is stationary in a wider sense. Okay. So, now we look at the actual definition of this. So, a time series is said to be covariant stationary if its first and second moments or first and second order moments are unaffected by change of time origin. So, one very important point to mention here is that as opposed to strong stationarity, which focus more on the overall distribution on the entire series, we do not have any such assumption here. So, the only assumption we require is that the first and second moments should be unaffected by time. Now, what do you actually mean by first and second moments? So, that we described in the last lecture. So, the mean function or the variance function or the autocovariance function or the autocorrelation function. Okay. So, weak stationary process only focuses majorly on these two, or rather these four entities. And again, just to summarize, there is no assumption on the distribution sense. Hence, we are putting some weaker assumption when it comes to stationarity, and hence it's called as weak stationarity. All right. Now, again, just to summarize as to what do you mean by moments. So, that means that we should have a constant mean and variance with covariance and correlation terms being functions of the time difference only. Okay. So, what exactly you mean by that? So, let us say you take a time series process yt, and let us say you want to find out the covariance between yt and probably yt plus k, something like that, alright, where k is the gap between the observations. So, yt is the observed time series at time point t, and yt plus k is the observed time series of the same time series, of course, at time point t plus k. Alright. So, notation wise this would be nothing but gamma of t comma t plus k as per the notation, and if a time series process is weak stationary or covariant stationary, this should only depend upon the lag or the difference between the time points, which is nothing but k. So, this is the idea behind a time series being covariant stationary. So, the idea is that the final covariance that you see, or the final mean function that you see, or the final variance function that you see, should be entirely independent of the time, which is t, and it should only depend on the lag, which is k. So, again, I guess this slide is kind of a summary slide as to what exactly should be the assumption or the underlying assumption. So, firstly, we should require that the mean function should be completely free from t for all t. So, here since you do not see any t in the subscript, so mu is a constant, alright. Then the second assumption is the same, should be true for the variance function also. So, variance of yt should again be a constant, let us say sigma square, and of course, this is a very standard assumption to make. So, variance should be indeed finite. Okay. Now, when it comes to covariance or the correlation functions, again as described earlier, so let us say covariance between yt and yt plus k should be completely independent of t, and it should only depend on the lag, which is k. And exactly same thing is true for correlation. Okay. So, correlation between yt and yt plus k should be completely free from t, and it should only depend on the time lag, which is k. All right. So, if anybody tells you that I have kind of analyzed a time series which is stationary in general sense, so by stationary he or she actually means weak stationary, okay, and then not strong stationary. Okay. So, from now on throughout the rest of the course, if we mention that a time series process is either stationary or non-stationary, we are kind of implying weak stationarity always. All right. Okay. So, I think now is a very good time to explore this entire idea about a time series process being either stationary or non-stationary using some examples. Okay. So, we will discuss some 3 to 4 examples, and then depending on all the properties we have seen in the last slide. So, again just to summarize, I will go back. So, all of these are the properties pertaining to a stationary time series. So, mean function should be constant, variance should be constant, and covariance and correlation should be again free from the underlying time frame which is t, and they should only depend on the constant k. Okay. Now, how would you be able to prove such a thing? So, let us say if you are handling a very basic process, a basic time series, so how can you prove that the underlying time series is indeed stationary or non-stationary? Okay. So, I guess we will start with some very basic examples, and then we will again see some couple of advanced examples and then try to explore a bit here. Okay. So, initially consider a time series yt where yt is exactly equal to Et. Now, again I will say that Et is a pretty standard notation which people use in time series terminology. So, what exactly you mean by Et? So, again I do not know how many of you have undergone a regression course, but in regression the model that we have, which is y equal to x beta plus epsilon, right. So, an epsilon that you have in the end is nothing but random error, is not it? Similarly, here we will say that ETs are a bunch of random errors. Okay. More specifically, we will say that ET follows some distribution, but they have to be IID. So, ETs have to be identical and independent both, with some fixed mean 0 and some fixed variance which is sigma square, right. So, again just to summarize, what exactly do you mean by ET? So, ET is nothing but a vector consisting of random errors coming from any distribution. It may be normal or exponential, gamma, etc., but the key assumption is that they should be IID. So, all the ETs are independent and identical, and then we can actually fix some constant mean. So, for trivial purposes we will fixing 0 as the mean and some constant variance, sigma square is the variance. Okay. Now, the important question is this process stationary or non-stationary? Okay. So, probably we can pause here for half a minute, and then you can actually think on this question as to how would you solve. Connection here is that you have to rely on all the properties we have seen on the last slide. Okay. Alright, so maybe you can start with the solution. So, the first key assumption is that the expected value or the mean should be free from t. Okay. So, if you find out the expected value of Et, which is nothing but the average here, so how much is that? So, how much is the mean of Et? So, through this assumption one can see that the mean is nothing but 0, right. So, we kind of assume that. So, mean is 0, and 0 is of course a constant. So, it does not depend on t, is not it. So, we are done with the first property, that the mean function of Et should be free from t. Okay. Now, firstly just one more point to add here if you may, is that we have to start by looking at the expected value of the actual time series, which is yt. But since in this case yt is exactly equal to Et, we can write down expected value of Et instead, which is 0. Hope this is clear. Now, talking about the second point. So, what should be true? So, secondly, variance of yt should also be free from t, alright. So, if you write down variance of yt, which is nothing but variance of Et, because yt is exactly equal to Et. Now, how much is that? So, again as per the assumption that we have taken, variance of Et is again a constant which is sigma square, alright. So, I can write down sigma square here, and again sigma square is clearly free from t. So, variance also does not depend on t. So, I think we are done with the first two properties. Now, the only other property which is remaining is to find out the covariance. Okay. So, how would you proceed with that? So, let us say we can write down something like covariance between Et and let us say some Et plus k for any k, is not it. So, we can write down covariance between Et and then Et plus k for any k. Of course, k should not be equal to 0, because otherwise it will be the variance, right. Now, how much is that? So, again as per the assumption that we have taken, all the ETs are IID. So, what do you mean by that? So, all the ETs are independent in themselves. So, if you take any two iterations of the same ET process, so let us say ET and then ET plus 1 or ET and then ET plus 2, right, or ET and then ET plus 5, you will get an independent structure. So, for any k other than 0, this covariance should also be equal to 0 because they are independent, alright. And again this 0 is completely free from t. So, this is one idea as to how one can easily prove that the underlying time series process, which is ET in this case, is stationary or not, right. So, finally, what is the answer here? So, answer is yes, yt equal to ET is indeed stationary. Okay. So, do not worry. So, we have other examples also. So, the next example is slightly involved, slightly advanced. So, consider a time series yt where the structure is as follows. So, yt equals Et plus 1/2 Et minus 1, alright. And what exactly is Et? So, Et is nothing but again the same structure. So, ETs are random errors, they are IID coming from some mean 0 and some fixed variance which is sigma square. And again the question is this process stationary or not, alright. So, is this process stationary or not, okay. Now, again probably what we can do is we can again start with the first assumption. So, first assumption is you have to check for the mean function. So, mean function of yt, which is nothing but the mean function of the process yt. So, in this case yt happens to be Et plus 1/2 Et minus 1 as per the equation, alright. Now, again remember what the other underlying assumption is. So, again ETs are what? So, ETs are random errors, they are IID with fixed mean which is 0, okay. So, since all of us know that mean is kind of linear, we can actually split this into two parts. So, this will be expectation of Et plus 0.5 expectation of Et minus 1, alright. So, expected value of Et plus 0.5 expectation of Et minus 1, and each individual expectation has 0 as per the assumption, okay. So, this would be nothing but 0 plus 0 which is 0, alright. So, this way we are done with the first property, okay. Now, talking about the second property. So, second property what we require the variance function of yt to be again a constant. So, variance of yt in this case is variance of Et plus 1/2 Et minus 1. Now, using all the properties of variance, so how do you split this variance and so on and so forth? I can write down variance of Et plus, since half is a constant, it will come out with a square, right. So, it will be 0.5 square variance of Et minus 1 plus 2 times covariance of Et comma 0.5 Et minus 1, isn't it? Now, again just to repeat very quickly. So, we require what? So, we require the variance to be also a constant function. So, in this case variance happens to be variance of the actual model which is Et plus 1/2 Et minus 1, which is nothing but variance of Et plus 1/2 square variance of Et minus 1 plus 2 times covariance of Et and 1/2 Et minus 1. Okay. Now, let us evaluate this individually. So, how much is variance of Et? So, again as per assumption variance of Et is nothing but sigma square, alright. So, this would be sigma square plus 0.5 square happens to be 0.25, and again variance of Et minus 1 is also sigma square, because remember one thing, this is true for all t, right. So, Et is a sequence, Et is a random sequence. So, for any t, let us say t minus 1 or t minus 2 or for that matter t plus 1, t plus 2. So, for any subscript here all the variances are similar and then equal to sigma square, okay. So, I can write down sigma square here, and now lastly how about the covariance. So, since these two subscripts are different, so Et and then Et minus 1, and since Et is a random sequence which is independent, the covariance term happens to be 0. So, eventually how much is this? So, this is sigma square plus 0.25 sigma square, which is 1.25 into sigma square. But the key assumption here or the key conclusion is that 1.25 sigma square is again free from t. So, you do not see any subscript here. So, hence we are actually done with the second point also. Okay. So, here I will give you one short homework kind of a thing. So, maybe once this session is over you can go back and then try it out. So, we require one more assumption though, if you remember, which is the third assumption in our case, that you have to actually show that covariance between yt and any other time point, which is yt plus k, should also be entirely free from t. So, if you see k in the equation, that should be fine, but the covariance or the correlation functions should be free from the subscript which is t. Okay. So, try this out. So, try this out. So, rather than me explaining each and every point, I think it will be slightly better that if you can actually write down on a piece of paper and then try to evaluate this quantity, okay, carefully. So, again just to repeat, what has to be shown? So, you have to show that the covariance between yt and yt plus k is again free from t, all right. Is this true or not true? All right. Okay. So, we will talk about one more example, which is kind of a very easy example to look at in the first sense, and why is that? We will see. So, consider a time series yt where yt is nothing but the sum of all these errors. So, E1 plus E2 plus E3 dot 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 up to Et. Okay. So, how many errors are we adding? So, we are actually adding t errors, right. So, we are adding t errors. So, yt is nothing but the sum of t errors. Okay. And again the same assumption with Et. So, Et is nothing but a random sequence which is IID, where mean is 0 and variance is sigma square. So, again the question is this process yt stationary? Okay. Now, I think this is a very easy task to show, and then you will see why. So, the first point is you have to actually show, or you have to actually find out if the mean function is constant or not, all right. So, how about the mean function? So, mean of yt is nothing but mean of E1 plus E2 plus dot 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 up to Et. Okay. So, E1 plus E2 plus dot 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 up to Et, all right. And then here what is happening is, since each of the means are zeros, right, since each of the means are zeros, right. So, we can actually write down that mean is also 0, all right. So, eventually the mean happens to be 0, all right. Is this okay so far? All right. So, we are done with the first point. Now, talking in terms of the second point. So, what has to be shown? We have to show that variance function of yt is again a constant. So, we will see what happens here. So, if you write down variance of yt, this is nothing but variance of this sum here. So, E1 plus E2 plus dot 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 up to Et. Okay. Now, remember one thing. So, how much is the variance of any Ei or any Et for that matter? So, as per the assumption, the variance of any Et for that matter is nothing but sigma square again. Okay. And then here, how many ETs are you adding, or how many errors are you adding? You are adding t errors. Okay. So, eventually the variance of this component should be nothing but t into sigma square. Hopefully, this is okay, because each variance is sigma square, each of the errors are independent. So, there is no question of covariance, because covariance term would be zeros, right, because ETs are IID. So, covariance terms are zeros, and then each variance is constant, which is sigma square, but how many? So, how many errors are we having? So, we have t errors, right. So, the variance function eventually happens to be t into sigma square, and then surprisingly this is not free from t, right, because you have a t component here. Okay. And hence the answer is that this process is not stationary. So, answer is no, right. And why is that? Because variance function we have seen is not free from t. Okay. All right. So, now I think we will see one last example, which is again simple, and then we will move on. So, let us say you have this last series yt, which is given by a plus bt plus some random error, which is Et. Okay. And the assumption is that a and b are constants, and Et has the same structure. So, ETs are IID with fixed mean 0 and fixed variance sigma square, all right. And then the question is yt stationary or not? Okay. Now, again I guess handling this example is again easy, you will see why. So, the first point is you have to see, or you have to make sure that the mean function of yt is free from t or not. Okay. So, what exactly is this? So, mean function of yt is nothing but expected value of the actual model that we have. So, a plus bt plus et. Okay. Now, remember one thing. So, expected value of any constant is the constant itself. Okay. So, since a and b are constants, we can actually write down a plus bt, because expectation of the constant would be the constant itself. And then how much is the expectation of et, which is the last term here, again 0. All right. So, this expectation actually boils down to a plus bt plus a 0, which is nothing but a plus bt. All right. But now the question is whether this expectation is free from t. The answer is no, clearly, because you have a t component here, right. So, again we are actually failing at the very first property itself. All right. So, again hence the answer is this process is not stationary again, and again why is that? Because the mean function itself is not free from t. Okay. So, hopefully this is okay. So, I just left one small homework for all of you. Again, just to repeat, if you go back in the second example, you have to actually show whether the covariance between yt and any other yt plus k for any k, of course, which is not equal to 0. So, if you want, you can mention it here that k should not be equal to 0. Okay. So, for any other value of k other than 0, is this covariance structure free from t or not? All right. So, through these all 4 examples, we have seen that whether a process is stationary or not, one can actually use a pen and paper and then try to simplify and then try to find out the answer. All right. Now, just to finish things off, so a few points regarding strong stationarity versus weak stationarity. So, does strong stationarity imply weak stationarity, or does weak stationarity imply strong stationarity, right? So, we have a few pointers here. Okay. Now, you should remember that strict stationarity or strong stationarity means that the joint distribution should depend on the lag, which is h or k, right. So, the joint distribution should be free from the time points t1, t2, t3 up to tk. So, the joint distribution should only depend on the lag, right. So, one point I have to make here is that strong stationarity is putting a stronger assumption, in the sense that it is required that the distribution should be free from t, right, or distribution should be time invariant, it should not be depending on t, whereas weak stationarity implies that the moment should be free from t. Okay. So, we are not making any assumption regarding the distribution structure when it comes to weak stationarity. Okay. Now, finite variance is not assumed in the definition of strong stationarity, we do not assume that. Therefore, strong stationarity or strict stationarity does not necessarily imply weak stationarity. And why is that? So, I think some of you might have heard about a distribution called as Cauchy. So, you have a distribution in statistics called as Cauchy distribution, and it so turns out that the mean function and the variance function of the Cauchy distribution does not exist. All right. So, even if you have a structure which is Cauchy, and if the time series process is strong stationary, it will not imply weak stationary, because the moments are not existing, isn't it? Because remember what we require for weak stationary, we require that the first moment and the second moment should be free from t. But since the moments itself are not existing for a Cauchy distribution, right. So, there is no question of implying weak stationarity there. All right. The third point is, if you have a non-linear function of a strong stationary variable, it would still be strictly stationary, but this is not the case for weak stationary. Okay. For example, the square of a covariant stationary process or weak stationary process may not have finite variance. So, think of a situation, just to explain this point, is that, so even if yt happens to be finite variance, right, but the square of the weak stationary process may not have finite variance. So, if you take any non-linear function of a weak stationary process, so let us say yt and then for example yt square or something like that, but it may turn out that the variance of yt square may not have finite variance. So, since it does not have finite variance, the second moment is ruled out. Okay. And last point is, weak stationarity usually does not imply strict stationarity also, as higher moments of the process may depend on time t. All right. So, these are some properties, or these are some pointers regarding when can strict stationarity imply weak stationarity, right, or vice versa. All right. Now, coming from that point, we will discuss a very important thing in the next slide, which is this one, that if the underlying time series process xt, so again I have used a slightly different notation. So, xt is nothing but the same yt notation that we are following, right. So, if the underlying time series xt is a Gaussian time series. So, what do you mean by Gaussian time series? So, Gaussian time series means that the underlying distribution is a normal distribution, okay, or the underlying distribution functions are all multivariate normal. So, if you treat a vector, right. So, if you impose this extra normality assumption, then in that case weak stationarity also implies strict stationarity. So, I guess this is one very strong way where weak stationarity implies strong stationarity. And why is that? Because all of you know that for a multivariate normal distribution, or for that matter for any normal distribution, the first two moments completely characterize the distribution, right. So, if you want to define a normal distribution to somebody, then you only have to specify what the mean is and what the variance function is, alright. So, hence if the underlying distribution is Gaussian, which is again a normal distribution, so Gaussian means normal by the way, then we will say that weak stationarity also implies strict stationarity, okay. So, hopefully this is okay. And now kind of we will summarize as to what we mean by non-stationarity. So, now we are shifting slightly from stationarity to non-stationarity, because I guess non-stationarity is more important, because almost all the practical examples exhibit some non-stationarity. So, there could be either trend or seasonality or some pattern here and there, right. So, small definition is that if a process lacks stationarity or statistical equilibrium, it is called as non-stationary, right. And following are very important 3 points which amount to any time series being non-stationary. And what are they? So, firstly trend. So, if a time series has some trend, let us say upward trend or downward trend, then we can say that the time series is not stationary, okay. Or the second point is seasonality. So, if you have some repetitions due to some seasonal variations or cyclicality, right. So, again maybe something like that, right. Then again we can say that the time series is not stationary. And the last aspect is changing variance. So, changing variance, or in time series terminology we call this a heteroscedastic in nature, heteroscedasticity, alright. So, what do you mean by that? So, I will give you a very quick example here. So, let us say if the variance of the process is changing, so maybe something like that, okay. So, here can you observe that the variance initially is small, and as you go down the timeline the variance is increasing, alright. So, if you immediately observe any trend in the underlying time series or seasonality or changing variance, then you can actually safely say that the underlying time series is not stationary, alright. Okay, thank you.